Hello everyone, welcome to the course on electromagnetic theory and interference. In this session, we are going to start a new module called Magnetostatics. But before going to that, we will see about the energy density in electrostatic field, which is a continuation of module 1. And we will start the magnetostatics in the next session as per the course outline. So we are going to find the energy density in the electrostatic field. That means what do you mean by energy density? The amount of work done per unit volume. That is my energy density. This is our final expression. So we are going to find that and we will solve a problem based on that in this session. So to find the energy density, first we have to determine the energy present in the assembly of charges, how much energy is present. For that, first we have to compute the amount of work done necessary to assemble these charges. So suppose we are considering three charges Q1, Q2, Q3, and we are going to position it from in the empty space. Okay, so from no work is required to transfer, because since the space is empty, if I move a charge Q1 from infinity to the point P1, there is no work done, because it initially the space is charge free and there is no electric field. So the work done is zero, okay, in moving the charge Q1 from infinity to P1. Whereas if I want to move a charge Q2 from infinity to P2, what happens? This work done is equal to product of the charge Q2 and the potential at that charge due to the Q1 charge. And similarly, the work done in positioning Q3 at P3, okay, is equal to product of the charge Q3 and potential at 3 due to the charge Q1 and potential at point 3 P3 due to the charge Q2. Okay, due to the presence of other charges, there will be a potential acting on it. And if the charges are positioned in reverse order also, we can write. Initially we started with Q1, right now we start with Q3. Okay, when we initially the space is empty, we are moving the charge Q3 from infinity to the point P, means there is no work done, zero. And Q2 we are moving, means the work done is product of Q2 into potential at P2 due to the presence of Q3. So it is V23. Similarly, for moving the charge Q1 to P1, what is the work done? It is Q1 into potential at P1 due to Q2 plus potential at P1 due to Q3. These are the things. So I can write two such equations, okay, and I can add these two, okay. At the left hand side we get 2WE, at the right hand side we get Q1 into this term, Q2 is common here, Q2 into V21 plus V23, Q3 into V31 plus V32, okay. So I'm just writing V12 plus V13 as V1, V21 plus V23 is V2. Similarly, for this term, it is V3. So if I want to find the work done, it is half of the sum of the product of the charge and potential at each points P1, P2, P3, right? Now this is for three charges, right? If I want to extend this for n number of charges, the work done is half Qk into Vk. Where let us now recap the two slides that we discussed so far. So to find the electric energy density in electrostatic fields, what we have done, we have started with moving the charge, okay, 3-point charges we have considered, and we are moving the charges in order, okay, from infinity to a point where in a space where there are initially no charges. Okay, then we have summed up to find the total work done. Then we have extended this concept to n number of charges, and we have replaced the point charges by continuous charge distribution. And especially from the volume charge density, that relation, we are going to apply the Maxwell first equation, that is del dot D equal to rho V. And we are in this step. So still we have not our finding of energy density. So to do that, we are going to use our identity. That is, there is two things, right? Del dot d v. Okay, there is a vector as well as a scalar. Electric density d is a vector, potential is v is a scalar. So for any vector and scalar, generally what we are writing is the divergence of scalar vector is equal to vector dot gradient of scalar plus scalar into divergence of vector. So we are interested in finding divergence of vector, right, in our work done. So I'm going to just keep this in right hand side and move the other terms to left. So this become negative. So I'm going to substitute that instead of del dot d. Okay, I am going to substitute del dot v is same. Only for a I have to replace with d vector into dv is there initially minus half of integral over the volume. Then I have to substitute d dot del v into dv. And now we are going to apply the divergence theorem to the first term. To this term, we are going to apply the divergence theorem. Divergence theorem states that the divergence of a vector field, okay, over a volume integral is equal to a closed surface integral of that same quantity over a surface. So this quantity v into t only I'm taking and I'm integrating over the closed surface, and this is there. Now what you're going to do is, we already know that relation between v, right? V is inversely proportional to r. Here d is inversely proportional to r square for the point charge distribution. So Vd is the first term right here. Vd is the first term, and if I product both, it will be 1 by r cube will be coming. And so this first integral, that is in the previous equation, this integral turns out to be 0. And I'm left with minus 1 by 2 integral over v d dot del v into dv. And we already know the relation E equal to minus del v. So I'm substituting here minus for minus del v, I'm substituting E because already negative is there. And now if I substitute in place of ds epsilon naught E, I will get half of integral over the volume epsilon naught E square into dv, right? For the electrostatic energy density, this is a work done. Energy density, this the electrostatic energy. This is the electrostatic energy or the work done, I can say. But electrostatic energy density means I have to compute the electrostatic energy, differentiate that electrostatic energy with respect to the particular volume. Okay. So if I take the differentiation, this integral goes off and I will get half into d dot e vector. So for d, if I substitute epsilon naught e, I will get epsilon naught e square, or I can write in other way also. Okay, instead of e, I can substitute d by epsilon naught, so I will get a d square by 2 epsilon naught. Okay, this is my final expression for electrostatic energy density, with the unit is joules per meter cube, because it is the work done or energy, electrostatic energy per unit volume. Okay. Now let us do one problem based on this. So problem, the point charges are given, 3 point charges. So we are labeling it as Q1, Q2, Q3, and these charges are located at position vectors R1, R2 and R3 vector. We are asked to find the energy in the system. To find the energy in the system, we are for finding the work done. So work done, W1, W2, W3. Work done in moving the charge Q1 from infinity to the point P, where there is no charge initially in that space. So the work done is 0. Coming to W2, it is product of Q2 into potential at V2, point P2, due to the charge Q1. So due to the charge Q1 only, we are writing the potential at P2, right? So Q1 divided by, as per this formula, 4 pi epsilon naught R2 minus R1. Okay, vector the magnitude of it, because we are interested in finding the potential at point P2. Similarly, for Q3, it is going to be this is third charge. So due to the presence of first and second charge, there will be a different work done experience. So it is Q3 is common in this case. So divided by 4 pi epsilon, we are taking it out. And Q1 is for the first term for V31. It is a potential at zero point 0.3 due to the charge Q1. So it is R divided by magnitude of R3 minus R1 plus for V32 it is the potential at P3 due to the presence of charge Q2. So Q2 divided by R3 minus R2. If you find the magnitude in the denominator term, here 1 minus 1 is going to be 1, magnitude of it is going to 1. So there is no denominator term here. Similarly in this term also. Whereas here if you see the coordinates will be 1, 0, minus 1. So taking the root magnitude of that, I will get root 2. And if I substitute Q1, Q2, Q3 values, and for 1 by 4 pi epsilon naught 9 is 10 power 9. Okay, and I do the simplification, I will get the energy in terms of nanojoules. I hope you learned how to solve this problem and how to find the energy density in electrostatic system. So let us meet in the next session. Thank you everyone.